So, good evening, everyone. I am Devadan Banerjee. Welcome to the second live session of Advanced Reaction Engineering. I am a PMRF scholar from IIT Delhi. So, in this week's discussion, we first will see the effect of pressure drop. So, in case of packed bed reactor, the conversion is a function of the weight of the catalyst, and the pressure drop, the pressure is a function of the weight of the catalyst as well. Okay, so for determining the pressure drop of a packed bed reactor, it is important to note that the variation of the total pressure during a reaction is not affected significantly for a liquid phase reaction. Concentration is not a function of pressure. However, the change of pressure in a gas phase reaction affects its concentration, conversion, and the rate of the reaction. So, concentration is directly related to the partial pressure of component. Therefore, concentration is a function of pressure. The pressure drop of a packed bed reactor. So if you see, so this is the design equation. If N naught dxdw equals to minus RA dashed. So if for this particular case, in case of a packed bed reactor, X conversion is a function of weight of catalyst and pressure is a function of weight of catalyst. Okay, so if for this kind of system in a packed bed reactor, you have to calculate the pressure drop in the catalyst bed of the reactor. So from that, how do you calculate? So for batch system, the volume can be written as V equals to V naught P naught by P 1 plus epsilon x T by T naught. Okay. Now the concentration is the ratio of FA by V. Okay. So now the stoichiometric coefficient also we know. Va equals to -1, Vb equals to minus B by A, Vc equals to C by A, Vd equals to D by A. And the molar flow rate of species A is Fa equals to Fa naught plus Vi Fa naught into X. And for flow system, what it will be? For flow system, it will be express the volumetric flow rate as a function of conversion. Okay, instead of the volume, we have to make it write in terms of volumetric flow rate. So from that, Ca equals to Fa naught into 1 minus X divided by V naught P by P naught by P 1 plus epsilon X T by T naught. Just have to, so instead of small b, you have to just replace it with this large thing, and then ultimately you can get to this particular formula equals to Ca naught 1 minus X by 1 plus epsilon X T naught by T into P by P naught. Now for example, consider reaction 2A gives B plus C. The rate law is minus RA dash equals to K Ca square. Ca equals to Ca naught 1 minus X by 1 plus epsilon X into T naught by T into P by P naught. Now minus RA equals to what it will be? Obviously Ca formula I have got, just replace it. So K into Ca naught into 1 minus X by 1 plus epsilon X T naught by T P by P naught whole square. And then instead of minus RA dash, you have to put Fa naught dx dw. Now again, F A naught value you know is equals to C A naught into V naught. So again, instead of F A naught, you can put C A naught V naught, or you can, and then you can just cancel it some X C A naught. So in that way, you can get here. So rearrange it. So one C A naught will be there in the right hand side. K C A naught by V naught into 1 minus X by 1 plus epsilon X T naught by T into P by P naught whole square. So dx dw equals to K C A naught by V naught into 1 minus X by 1 plus epsilon X whole square into P by P naught square. Then based on that, you can get the catalyst weight conversion pressure drop related by this above equation. The conversion X can be found as a function of catalyst weight, right? So with different X, you can have different W, and then based on that, you can have different of these particular conversions and pressure drop. You can calculate that. So most of the gas phase reaction are catalyzed by passing the reactant through a packed bed of catalyst particle. The expected packed bed reactor system must be zero pressure drop, which is delta P equals to zero. However, in real cases, the pressure drop exists once catalyst is placed in the reactor, which means that delta P equals to positive. If delta pressure drop is positive, then the actual conversion is smaller than expected if we neglect the pressure drop. Okay, very understandable. So now the Argon equation is to calculate or measure the pressure drop in a packed bed of porous catalytic bed in a reactor. dPdz equals to minus G by rho GCdP 1 minus 5 by 5 cube into 150 1 minus 5 mu by dP plus 1.75 G. So for laminar flow, the first term is dominated, and for turbulent flow, the second term is dominated, right? Now, what are the significances of these different uh, terms? We all know phi is porosity, which is nothing but the void fraction, the ratio of void volume by total bed volume. Now, 1 minus 5 will be the solid volume by total bed volume. Gc is the gravity conversion factor. Okay. So the next lecture is basically again continuation on the effect of pressure drop on reactor design. For the packed bed reactor, the gas density rho is something which varies in the pressure P in argon equation. So you have to calculate the pressure drop in the catalyst bed of the reactor. The reactor operates at the steady state. So M equals to the mass flow rate and M naught equals to the entering flow rate. So at steady state, M naught equals to M0 dot rho 0 V0 equals to rho V. We know V equals to V0 P naught by P 1 plus epsilon x T by T naught. So you have to substitute in equation 2 this particular entire term of V. Okay. Equation 2 is this rho 0 V0 equals to rho V. So rho 0 V0. So rho equals to what? Rho 0 V0 by V. So put V this particular terminology in place of V and you will get this rho naught P by P naught 1 plus 1 by 1 plus epsilon x T naught by T. Okay. Now if you can see here basically Ft by Ft naught is nothing but equals to 1 plus epsilon x. You can prove it in this way. And then 1 by 1 plus epsilon x you can just put it 1 by Ft by Ft naught means Ft naught by Ft. So in this way I am getting the rho value of rho. Now substitute the rho in argon equation. This is your argon equation, right? So substitute rho. You get this kind of terminology. So this entire thing which might be known is termed as beta naught. So it will be minus beta naught P naught by P T by Ft naught T by T naught. Now basically Z is the reactor length and W is the catalyst weight. So what is W? W is nothing but 1 minus 5 is AC into Z. AC is cross sectional area. Z is reactor length. Rho C is solid catalyst density. Okay, so dpdw equals to comes at this particular expression, and then we have to simplify it. dpdw equals to minus alpha by 2 p naught by p naught t by ft naught t by t naught. What is alpha? Alpha is proportional to the beta naught. 2 equals to 2 beta naught ac by rho c 1 minus 5 p naught. Okay. So ultimately this is basically the differential form of Argand equation for the pressure drop in a packed bed reactor in a PBR packed bed reactor. Okay. dy dw equals to minus alpha by 2y 1 plus epsilon x t by t naught. So there are these limiting conditions. If epsilon would be 0, if then there is no volume or volumetric flow change. Case 1, if epsilon equals to negative, the pressure drop delta P will be less than that for epsilon equals to 0. If epsilon equals to positive, the pressure drop delta P will be greater than that for epsilon equals to 0. Okay. Now the effect of pressure drop in packed bed reactor, analytical solution of differential equations. Okay. Differential equation. The Arkan equation is dx dw equals to kc naught by v naught into 1 minus x by 1 plus epsilon x is the whole square to p by p naught is whole square, and dy dw equals to minus alpha by 2y into 1 plus epsilon x t by t naught. So if epsilon equals to 0 and this is an isothermal operation means t equals to t naught, then the equation can be written as dy dw equals to minus alpha by 2y where p by p naught equals to y, and then after rearranging and putting y inside the derivative integrating, uh, you'll get this y equals to p by p naught equals to 1 minus alpha w uh, all to the power half. So dy dw equals to minus alpha by 2y into 1 plus epsilon x t by t naught minus r dash equals to k c naught 1 minus x by 1 plus epsilon x t naught by t p by p naught whole square. Okay. So ultimately substituting p by p naught in the rate equation, you can get this kind of equation. Dx dw equals to k c naught by v naught 1 minus x by 1 plus epsilon x whole square p by p naught whole square. And then if you have to express the pressure in terms of the reactor length, then you can have this p by p naught equals to 1 minus 2 beta naught z by p naught. Okay. Okay. Now that was from the first case. If children goes to 0, and then if children goes to not equals to 0, then you will have this equation d1 dw equals to minus alpha by 2y into 1 plus epsilon x t by t naught. This equation can be solved numerically. Okay. The pressure gradually decreased or pressure drop increased with increasing catalyst weight W. The rate of reaction of Ca is always lower or smaller than the case with no pressure drop. Therefore, conversion will drop due to pressure drop. Okay. So in these particular graphs, it has been shown that what will happen if there is no pressure drop and there is some pressure drop. Right. So if W neglect pressure drop, then actual conversion turns out to be smaller. Therefore, we should design reactor such a way and design the catalyst particle in such a way that there is no pressure drop. Okay. Then they have to see some examples for analytical solution or reaction with some pressure drops. Okay. So basically, how to solve this kind of equation for with pressure drop? We have shown here. Like step one, mole balance you have to do. Then the step two to write the rate law and then substitute in step one. Then step three, stoichiometry, concentration in terms of the conversion. And then the step four, F N of dxdw equals to minus R dash equals to Kc naught square 1 minus X whole square 1 minus alpha W to the power half whole square. And then you have to solve for it, solve for catalyst weight. So catalyst weight for second order reaction impact bed reactor pressure drop delta P W equals to 1 minus into 1 minus into 1 minus 2 V naught alpha by Kc naught x by f1 minus x whole to the power half divided by alpha. Okay. And then if we increase the catalyst size by a factor of 2, what will happen? So dp2 equals to 2 dp1, what will happen? These are basically the examples. So you have to make sure the okay. In a similar way, there are these different examples which have shown. So what will happen if the diameter is increased or the diameter decreased? So based on this particular equation, so ultimately the result is the conversion will increase as increasing the catalyst particle diameter. Since the interparticle diffusion is important in the catalyst period, we cannot neglect. For larger particle size, takes longer time for a given number of reactant and product molecules to diffuse in and out of the catalyst particle when they undergo reaction. Therefore, we have to select an optimum catalyst particle size. Okay. So a low conversion is observed at both small and large particle diameter. So for small particle diameter, there will be high pressure drop. Large particle diameter, there will be internal diffusion. You have to choose an optimum diameter in between to operate the packed reactor with highest conversion. If we use larger diameter tube and put catalyst on it, then the channeling and bypass dominates as a result of low conversion. Okay, and these are the final like continuation of these examples. Calculation of weight for conversion in a reactor with pressure drop. Okay, there are different examples have been shown. I hope you will go through these examples. I'm not going through them. And if you have any concerns, we might discuss. Okay, thank you.